This is Geometry Lessons 6.1, Reflection Symmetry. So we have spent a great amount of time looking at reflections, combinations of reflections, and we're going to continue with that now, but talk specifically about symmetry of shapes and how that can be represented as a reflection. And because of that, what special things can we deduce theorems for? Based on these symmetric figures, so on and so forth. So the big idea says common basic figures of geometry like segments, angles, circles, they all have reflection symmetry, and we're going to study what makes those special because they have symmetry. So I'm sure you've heard the word symmetrical before, maybe even as early as elementary school, maybe in art class or somewhere else where something is symmetric. So specific to geometry, it's going to be similar to the way you've understood it in the past, but when a figure is reflected over a line, there are times when the figure will coincide with its image, meaning you reflect something over a line and you end up with the exact same thing you started with. So it flips, but it's still exactly the same. So consider the lion face shown at the right. When we reflect figure C over line L, so we're going to call the lion figure C. If you take a look, if we put line L right down the middle of this, and we go ahead and we flip it, so everything on this side comes over here, everything on this side comes over here. It basically spins around. So when we reflect figure C over line L, the image and the pre-image are identical. You end up with exactly what you started with. Okay, so in terms of the notation, that is saying that reflecting figure C over line L results in figure C. Therefore, C is a reflection symmetric figure. So a reflection symmetric figure is one that when you reflect it over a line, you end up with what you started with. Here's your definition, a little more complicated than I just stated. A plane figure F is a reflection symmetric figure if and only if there's a line M such that reflecting figure F over line M results in figure F again. The line M is a symmetry line for the figure. So we would say line L is the line of symmetry or a symmetry line of figure C, the lion. All right, so let's take a look at these three groups of letters and talk about how much symmetry they have. Do they have symmetry? They're grouped because they're all similar in their groups. If we look at group one, if you try to draw a line of symmetry, a line where it goes straight down, it cuts it in half basically, and both sides are going to be the same, just the mirror image, you're not going to be able to do it. Now the K almost looks like you can do it, but a true K is not going to be the same on both sides. If you look at, say, G, if I reflect over that line, it's not symmetrical. If I try to cut F this way and I folded it over that line, it's not going to fold over on top of itself. Okay, so none are symmetric. Two M's in symmetric. All right, group two, I do start to see some symmetry. So I can cut A straight down the middle, and if I reflect across this line, I end up with exactly what I started with. Imagine again folding it across this line. It should fold over on itself. You may look at B and say, well, that doesn't work, but it does if I go this way. Okay, straight across, B could be folded on itself. C straight across can be folded. D straight across. E straight across. M not straight across. That's not going to work. If I folded M across this line, it's not going to line up. But I can fold M over this line. T would be over this line. U would be over this line. V would be over this line. W over this line and Y over this line. But if you notice, each one of these has only one line of symmetry. In group three, we take a look now. We have two lines of symmetry for each one of these letters. H can be cut across like this, but it also can be cut across like this. And either way, when I fold it or reflect it over that line, I end up with what I started with. Same with I can go down or I can go across. Perfectly cuts it in half. It's a bisector. You can fold over it. O has both of those. And X also has both of those. So we would say 2 lines of symmetry for this group. Okay, so we've actually talked about this next theorem. We've just not given it a name. The flip-flop theorem says if I reflect a figure over a line and then I reflect that image back over the line, I get back to the pre-image. That's what the flip-flop theorem says. So as we start building proofs, we can use this theorem. It says if f and g are points, we reflect f over line L and we get g. Then we know that if we reflect g over line L, we get f. And the opposite then is true. So if they are figures and we reflect f over L, we get g. Then the reflection of g, that actually says, okay, so, sorry. These do kind of say the same thing. We're starting with f and go into g, and then if we get g, we go to f. One's talking about points and one's talking about figures. So you've got those two examples here. So just want to make sure it's not something that you in your mind you think is specific to just points or just figures. They're all going to fall under this. So if I reflect f over line L and I get g, if I go ahead and reflect g back over line L, I get f back where I started. And this will hold true both for points and for figures. All right, now let's start to take a look at segments, circles, figures. Where are their lines of reflection? Where is their reflection symmetry? So we're going to start with segments. It says how many lines of symmetry are there for the segment shown. The obvious one that everybody sees is a special line we've been talking about. This would be your perpendicular bisector that cuts this perfectly into two pieces. If I reflected over that line, we've talked about a perpendicular bisector is a line of reflection. H becomes the reflection of P over this line, which is the perpendicular bisector. But there is another one, the not so obvious one, that is actually the line that contains the segment. You might say, well, it's not on both sides, so is that really symmetry? But according to our reflection theorem, if I go ahead and reflect this segment over this line, do I end up with what I started? And yes, because every point that's on that segment is also on this reflection line. We know when you reflect a point that's on the line, it doesn't move. So this is a line of symmetry because when I reflect it, okay, I still end up with the original shape. So this theorem says, segment symmetry theorem says, every segment has two symmetry lines, the line that contains the segment and the perpendicular bisector. All right, so that's reflection symmetry for segments. Well, what about angles? Let's take a look at those. Okay, so where is the line of symmetry for an angle? So similar to a segment, the bisector is going to be the line of symmetry. If I construct the perfect angle bisector, which we've done with the compass already, when I fold this over that line or reflect it over that line, I do get the original shape. And so you can see here, this is the angle bisector with angle 1 equaling angle 2. That's going to be your line of symmetry. So your two theorems that talk about that is your side switching theorem. It says if one side of an angle is reflected over the line containing the angle bisector, excuse me, its image is the other side of the angle. And then this other theorem kind of just explains it differently, kind of going the other direction. Angle symmetry theorem says the line containing the bisector of an angle is the symmetry line of the angle. Okay, so they're each talking about the same thing. One is starting with the line and one is starting with the angle. But basically, we just need to make sure we understand the line that is the angle bisector is a point of symmetry for the angle. If I reflect over that line, I still get the original angle. That's why it's symmetric. All right, how about circles? If I asked you to draw all of the lines of symmetry of a circle, you would not be able to do it because a circle has an infinite number of symmetry lines. You can just keep going on and on and on. There is not a finite or an exact amount of lines that create symmetry for a circle. Any line that passes through the center of the circle is a symmetry line for it. So you've got this one drawn right here through the center. I could draw another one through the center this way. And again, if I fold over or reflect over that line, I still have the same circle. I can draw it this way. As long as it goes through the circle, through the center of the circle, it'll be a line of symmetry. If I were to just draw a random line like this through here and then fold over that line, clearly that is not a line of symmetry because this is not going to line up. But if it goes through the center and I fold it, I do get back to the original shape. So the circle symmetry theorem says a circle is reflection symmetric to any line through its center. All right, so why have we looked at these couple different figures and talked about reflection symmetry? Why is this important? So a reflection symmetric figure is also congruent to itself, right? That's the whole point. It's congruent to itself, congruent meaning the same size. So it becomes itself. Because a reflection symmetric figure is its own image under a reflection, it's congruent to itself in a non-trivial way. Its parts can correspond to different parts of itself. So here's where we're going. The symmetric figures theorem says if a figure is symmetric, then any pair of corresponding parts is congruent. And this now starts to filter back to what we were working on. We had two congruent figures before, and we talked about corresponding parts being equal to each other or congruent. Well, when we have these figures that are symmetric, the corresponding parts over those lines of symmetry are equal or are congruent, and we are now allowed to state that. So here's example number 2. I've got this shape, kind of looks like a cat, dog, who knows, but this is symmetric. And then they tell you the polygon at the right is reflection symmetric over line QH. So here's Q and H. If I draw that line through Q and through H, it perfectly cuts this shape in half. I can reflect over this line and I get the same shape. So that's what makes it reflection symmetric. So this new theorem now says, well, since I reflect this and I come over here and I get this, they must be congruent to each other. So name several congruent angles, sides, and diagonals. Okay, so we're basically going to be looking at these almost like two different shapes that are congruent to each other. Just the right side and the left side. Separate them and think about them as two separate shapes, but when I reflect, I get the congruent other side. And so that means angle A is the same as angle O. Okay, so angle A is congruent to angle O. Angle C. Now this is a little bit of a different looking angle, right? More than 180. But regardless, that measurement is going to be the same here as M. So angle C is congruent to angle M. It's not just angles, it would also be segments. So down here, GH, segment GH will be congruent to IH. Okay, and I can go all the way around. I'm not going to do every single one, but like DE is going to match LK. And so when I have these symmetric shapes, if I'm given an angle or a side length over here, I am allowed to assume, if I know that it's reflection symmetric over that line, that I have corresponding parts here that are congruent on the other side. So that's what makes these special. Okay, so another example, same idea. This figure at the right is symmetric over SW. So if I draw this line, one side of the shape is a reflection or an image of the other side of the shape over that line. So angle Z equals angle T, or is congruent to. Remember, you would say equals if you actually had the measure. If this is 60 and this is 60, you'll say they're equal. We don't know the actual angle measurements, but we do know that they're the same size. So that's congruence as opposed to equality. So since we don't know the measurement, we can't say they're equal, but we do know, since this is reflection symmetric over this line, we know that they're the same size. So we can say that they are congruent. We know that they're equal. Okay, but again, that's talking about an exact measurement. Congruence is just talking about they are the same size. So let's finish this out. a couple more congruent angles, sides, and let's talk about diagonals too. So let's do some more angles. Let's do angle X. Right here would be congruent to angle V. If we're doing some segments, let's do ZY. It's congruent to. Now you want to be consistent when you name these. Don't say UT, even though that's the same length, right? Z corresponds with T. So since Z was in my first position, I need T in my first position. Y was my second position, which is the reflection of U over this line. And so U should be in the second position. So you do want to be consistent there. So if I go ZS, again, Z corresponds with T. So T has to go first. And S obviously corresponds with itself. Now we can also talk about diagonals. They don't have to be shapes that just stay on one side. If I have ZT, that's a diagonal. So let's label our diagonals here. ZT. When it gets reflected, it's going to be congruent to the new shape. But we wouldn't say ZT is congruent to ZT because that means the shape just stays exactly in the same position. But right, Z would come over here and T would come over here. So Z corresponds with T, so we're going to put T first. And then T would correspond with Z, so we put Z second. That could be a little confusing looking at it that way. Let's look at it a little differently. Let's go from the diagonal that goes from Y to T. Okay, when I flip that one, the T is going to go to the Z and the Y is going to go to the U. Right? It's going to end up looking like this if I reflect it over this line. So if I start with YT, the diagonal YT, it's going to be congruent to its reflection, but make sure you match up your corresponding parts. Y over this reflection line corresponds with the U, so you put it first. T over this reflection line corresponds with Z.